This is a tutorial on electromagnetic induction and the basic operation of how a transformer works. This is suitable particularly for high-level Year 11 students studying GCSE physics. In the OCR syllabus, this would be for P6, but it's also very good for helping people who are studying in Year 13 to discuss concepts surrounding electromagnetic induction. Typically, Year 13 pupils who do electromagnetic induction questions, they do very well with the mathematical questions, but find it very difficult to very difficult to actually describe the concept. So we start off with the idea of electromagnetic induction. I've got a coil of wire here with just two coils, with just two loops, and if I just go down to one loop, what you've got here is you've got an area inside that coil which is at right angles to the magnetic field, shown by these little compasses, and you've got one coil. Okay, so what you've got is you've got the magnetic flux density, which is the magnetic field strength, effectively, which you multiply by that cross-sectional area, and that gives you the magnetic flux. Now, as you change that magnetic flux, you induce a voltage. Okay, and the voltage will also then push a current through a resistor. It's very important when you're describing induction to actually say that you induce an EMF if you're an A-level student, or a voltage if you're a GCSE student, and then say that it will push a current through the resistance of the circuit. So we've got here a magnet. As I move the magnet closer, I'm going to change the magnetic field strength, which is going to be shown by the brightness of these little compasses. And it's also going to be shown, and it may even change the direction ever so slightly. Now, as the magnetic flux density changes, as the magnetic field strength changes, then so too will the magnetic flux inside that coil. Obviously, this is an A-level description. So change the magnetic flux density or magnetic field strength for a GCSE student. That would be to move the magnet closer, and as you move it closer, eventually induce an EMF, okay, a small voltage. So as I push it in, it goes one way, it's negative. As I pull it back out, it's positive. If I pass the magnet all the way through, it goes negative and then positive as it goes through, and then negative and positive as it goes back. And that's because the magnetic field strength is changing inside that coil, which is actually then creating a force on these electrons, which is making them move around, try to move around the wire. As you've got a complete circuit, they will start to move. The faster I move the magnet, the greater the current or greater the voltage I induce. Okay, and if I add more coils, then each area kind of adds together. Now, for the A-level explanation here, we're thinking about magnetic flux linkage, which is basically the magnetic flux multiplied by the number of turns on the coil. So now I have 3 turns on the coil, and I induce a far greater EMF as a result, 3 times the EMF effectively. So the other thing to think about is also the area. If I increase the area of the coil, then you're going to have more of the magnetic field changing inside that coil, which will therefore induce a even higher voltage, as you can see, or even higher EMF. So that's roughly how induction works. As you change the magnetic flux inside the coil, or magnetic flux linkage inside that coil, the rate of change of that magnetic flux is equal to the EMF or voltage induced. That would be Faraday's law. Remember, if you're doing an A-level question, if you're doing the mathematical questions, that's always a good place to start. You start with that first principle, and you probably won't go wrong. So that's the basics of how induction can work. If we move on to something like a generator to generate electricity, here I've got a water wheel, a spinning magnet, and I've got a coil of wire. Now, what happens with a generator is you've got the magnet, in this case, spinning. Sometimes it's the coil that spins, and it's connected via brushes and split rings or slip rings to a circuit. And just to show that there is a current flowing, I've got a light bulb here. So here we've got a rotating magnet. Now, inside this coil, there'll be these compasses will show you a continuously changing magnetic field, and it will show you a continuously changing force on those electrons. Whenever the magnetic flux is changing, then you're going to induce an EMF, which is going to try and pull electrons along, In this case, it's changing backwards and forwards. The electrons will be pushed from side to side as it changes. Remember, it's the rate of change that induces the EMF. So as I pour some water on, you can see it sort of rotating and changing the magnetic flux inside that coil. Obviously, this can be exaggerated if you put an iron core inside the coil, but I don't have the simulation for that. But so we just have to make do with being told. And as you can see, it's making the electrons move backwards and forwards. So it's inducing an alternating current. The current is changing direction as the magnet changes direction. The faster I spin the magnet, the higher the rate of change of magnetic flux density or magnetic flux inside the coil, the higher the EMF is induced, and in that case, the more current you've got, the brighter your bulb is. So as I spin it even faster, the rate of change has increased, so the frequency of the generated electricity has increased, but so too has the EMF. On to the last part, which is the transformer. Now here I've got a transformer, I've got my pickup coil here, and instead of using a magnet, I've got a battery and a coil, so it's an electromagnet. Now it stands to reason, if I place one inside the other, now the way you would ordinarily join these two coils together is via an iron core, but as I change the voltage, so I pass a current through, as I change the voltage, I induce an EMF. As soon as the voltage stops changing, the EMF goes down, induced in the secondary coil, goes down to 0. So if I change the other way, you can see that I induce an EMF going the other way. So if I increase it, the EMF induced is one way. If I change it the other way, the EMF induced changes it the other way. Okay, so it's only when you've got a continuously changing current in here, creates a changing magnetic field, which then induces an EMF inside the coil of the secondary coil. Okay, you can also do it by normal way by just moving the magnet in and out, but that's not really what we're demonstrating here. So I could then demonstrate it again with an alternating current, because you need a changing magnetic field. So as the current is going backwards and forwards, it then induces an EMF inside the secondary coil, and you can see that as the change goes from positive to negative, the needle goes one way. As it goes from negative to positive, the needle goes the other way. Okay, now you're not getting very much being induced here because you've not got it connected via an iron core, so you're getting what we call magnetic flux leakage. So not all the magnetic field that's being created by this current is actually going to be picked up by the area of this coil. So if I put that inside, so a high percentage of it is, you can actually see that it's creating or inducing an alternating current voltage, and that's roughly how a transformer works. Obviously, with transformers, if I have the same number of loops on the primary coil as the secondary coil, theoretically, I should get the same output voltage. And this won't be quite the same because I've got different areas, of course, but you get the idea. Okay, and as I decrease the number of coils on the secondary coil, you can see that my induced voltage decreases accordingly. So that is roughly how a transformer works, and also electromagnetic induction explained. So the idea is we have a changing magnetic field inside the coil, then induces an EMF, which then drives a current. The key idea here is that we're changing the magnetic field, which you can use to generate electricity by rotating a magnet. It creates a changing magnetic field, continuously changing backwards and forwards, to create an alternating current inside the coil of wire. I can actually show you with the voltmeter there. Okay, and the last one is instead of using a rotating magnet or putting a magnet in and out of a coil, what you can do is create that change just by passing an alternating current through a primary coil, which will then induce, and that changing magnetic field will then induce the EMF, the alternating EMF across the secondary coil. And that is roughly how we go from the basics of electromagnetic induction to how a transformer works.